I first came to CMAT about 20 years ago to teach a workshop, and at the invitation of Graciela and Rogelio, who is sitting somewhere back there. Oh, okay. Right. And then I've been here once again, and then it's a pleasure to be here. And I want to thank Victor for the organizing committee for the invitation to come. When Victor asked me to talk, I gave him two options. One is this title or some variation of it. And then I gave him a title on what I'm working on right now. By the way, I have moved to Wells Fargo. I'm in the process of moving from University of Michigan to Wells Fargo, which is in Charlotte, North Carolina, mainly because my granddaughters, or two granddaughters, who live in North Carolina. And as you get older, the most important thing is your grandkids. And so that's why I moved, and I think we haven't talked since then, right? So I gave Victor the option of talking about some statistics in banking, and he said no. So he asked me to talk about something on big data. Now, Professor Bose said that he doesn't work on high-dimensional data. Now, I don't work on big data either, but that doesn't stop me from giving talks. So as you get older, of course, you pretend that you're an expert in everything. And so I'm going to be talking about some aspects of big data, mostly dealing with statistics, or at least from the statistical perspective. And I'll also talk a little bit about data science. And I understand from Graciela that CMAT is also starting a master's program in data science. So this is emerging as a very important big area. Okay, so when I started thinking about big data about a few years ago, I went to Wikipedia, which is of course the source of all information, and I Googled and said, I guess you can't say Google, I wikied and said, what is big data? And I found this, big data is a music band. And how many of you know that? There is a band called Big Data. Yeah. And it sort of started in 2013, around the same time as the Big Data craze was getting up, right? And for those of you who are not married, still on the dating, so there is a song called Big Data that you might be interested in listening. So, what is big data? Now, all of you must have heard by now at least one talk, if not multiple talks on big data, and everybody goes around giving talks about big data. So if you have computer scientists talk about big data, a bit different than statisticians talk about big data. So this is just like the elephant and the three blind men. Everybody has their own version of what big data is. So what I'm going to be talking about is, as I said, statistical perspective. Now I would recommend, this is now a little bit old, this McKinsey Global Institute report on big data. It's about 2012, I believe. It's about 4 years old. Anybody interested, just please Google for that. So as they say, big data is the next frontier for innovation, competition, and productivity. So all this is a catchphrase or buzzword describing the data tsunami and this humongous amounts of data that are becoming available, are being collected, becoming available, and the potential benefits from what it is that we can do with the big data, and all the opportunities, the challenges, and from the data, and of course, the corresponding information revolution. Right? So let me just start talking about the myths about big data. As you all know, there are lots and lots of people in this space promising everything, right? That big data cures cancer, for instance, right? So there are lots of myths about big data, and I've organized my talk around some of these themes. So there is this article by this fellow called Samuel Arbesman, who's at the Kauffman Foundation. And he's actually got a very nice book called The Half-Life of Facts that you might want to take a look at. So there are a few of this that I picked up. The first thing is that we all know what big data means. Everybody says, what does big data mean? That is a clear definition. Big data is new. It's revolutionary. The bigger the data set, the better it is. The more information. And then, of course, the one here, people claiming that With big data, we don't need any scientific theories, right? The more data we have, we can solve, we can understand everything, we can solve all of this. So let me just go through that, weave that in my presentation. So there are many, if you go and sort of, Google, look at the web, there are many descriptions and many definitions. Some of them are a little crazy. But this is the one that I happen to like. Okay? It's actually, you can call it a definition, but actually it's sort of an elusive definition. McKinsey report that they quoted. Okay? It says big data refers to data sets whose size is beyond the ability of typical database software tools to capture, store, manage, and analyze. Okay? So that's what it says, right? But the next sentence is very revealing, and I really like that because this definition is intensively subjective. It incorporates a moving definition, meaning what is big data today will not be big data tomorrow because the technology is constantly changing. Our ability to analyze the data is changing. The data capacity, data transfer, all of these things are changing, right? So it's a moving definition, and I like that one. Okay? The other thing is that the notion of big data is also different by sector. What is big data in physics? Okay. Petabytes or what they call exabytes of data they're collecting, or astronomy. It's not the same in social sciences and surveys. Okay. What governments are doing, the data size are not of that same order of magnitude. Okay. So I like this definition for that particular purpose, right? So with that, those caveats, big data in many sectors will range from a few dozen terabytes to multiple petabytes. Okay. Now, the problem is now the issue is that this is about 2012. So now we are talking about exabytes, which is another thousands of petabytes. Okay. Now the other part is that those of you who have read this or sort of know about big data is that there are many dimensions to data. It's just not volume. You would have heard things like variety, which is the heterogeneity of data, the different data structures, volume, the speed with which we are collecting data. Right? So I'll mention that in a few minutes. Okay. Now the other myth is that big data is new and is revolutionary. Okay. Now it is not revolutionary, as I will see. It's actually incremental. The change in what we're seeing in big data is not revolutionary. It's actually incremental. So, is it really new? So I used to work at a place called Bell Labs, where a lot of these modern developments in data analysis started. There was a guy called John Tukey, many of you have heard, he was there. I was there at Princeton, it was split his time. So I sort of went to school at Berkeley, didn't really know any applied statistics, went to Bell Labs and learned everything, was all I know about applied statistics. So in the 1990s, we were talking about large data sets. And then it became massive data sets. So you see, in 1996, there was a US National Academy workshop called Massive Data Sets, in 1996. Now we've gone to big. Now, by any definition of the word, big is smaller than massive. Right. So why did we go from massive to big? That's because a lot of these things comes from people in industry. Some guys, probably in Silicon Valley, started saying, let's come up with this term called big data and make it into a, one of those big marketing slogan or whatever it is. I mean, if you actually Google, there is a particular, you can see that where the term, who first used the term big data, at least as far as. So the problem with statisticians is that, there was a recent 2013 US National Academy's panel that had a report called Frontiers in Massive Data Analysis. So we are still sticking with the term massive, and we're not actually catching on the term big, right? Big data. Now, if you haven't seen this report, I recommend that you read it. It actually was chaired by a committee, the chair of the committee was Michael Jordan from Berkeley. Many of you have heard of him. Not the basketball player. Okay, so let me just go back in time and give you my sort of view of what was happening starting in the 1980s or so. Okay? You all remember that there was, going back to 1980, there were massive, huge changes in the computing power, and also our ability to collect data, because data capture technologies, sensors, for instance, were becoming so cheap that people are beginning to collect data, lots and lots of data, but certainly not in the scale that we're facing right now. Okay? So because of these cheap data capture technologies, you know, your sensors and the RFIDs, there's been a steady increase in the amount of data that have been collected. And you can say that there's been a lot more in the last 10 years, explosion rates. Okay? Now, of course, there's a lot more computing power. What that means is that we can start using more flexible models. So you can remember things like, you know, people were beginning to use generalized additive models, Mars, splines, all of these became possible because of the added computing power in the 1980s. And we don't have to assume everything is linear or polynomial, everything is parametric. People are starting to use semi-parametric models, variant coefficient models, right? Non-parametric regression models, non-parametric density estimation. And this is all has been happening 1990s, since about 1990s, right? So for instance, you know, there's a very nice paper by John Tukey and Jerry Friedman called Projection Pursuit, which looks at, you know, different ways of reducing the dimension. And I believe that was before 1980. So looking at this data, that's becoming more and more data that is becoming available. So these I have to like a new research challenges and accomplishments even well before 2010, the last 6 years, when big data sort of caught on. And of course, statisticians have been working on it, and computer scientists, although the collaboration has been between statisticians and computer scientists hasn't been as extensive as we should have had and what's happening now. Okay? So let me just go through a few of these things just to, most of you will be familiar with this. I just wanted to remind us what, you know, what it is that we have done and what we have not done. So you can remember that there were lots and lots of excitements in the 1980s and 1990s about using the computer to do a lot more interesting stuff. So now, I just want to mention data mining is now, and people use the term data mining in a very loose sense. You know, what does data mining mean? Okay? People sort of mix up machine learning and data mining, and you know, and people sometimes they say data mining also includes supervised learning, unsupervised learning. Now, if you remember exploratory data analysis and the Green Book by Mosteller and Tukey, that was what, 1970s, right? So data mining is nothing more than EDA on steroids, right? That's what it is, right? You're looking at unusual patterns, unusual structure in the data. Okay? The thing is that we as statisticians, and one of the things that I think we didn't do ourselves a service, is that people like John Tukey said, you must understand the data. You must interact with the data. You must visualize the data. All the analysis we have to learn by interacting with data. What do computer scientists do? They have the mentality that, look, the data sets are big. They understand that people are too lazy. They don't want to interact with data. They want everything automated. They want everything given to them. So there is a lot more emphasis on automation, in part because the problems are big, in part because people do not have the interest to actually interact with the data. They just want quick answers. So data mining, and the earliest application of data mining was what's called pairwise association rules. And this was an algorithm that was developed by a guy called Agrawal in IBM. So the idea was that if I go to a grocery store and I buy milk, what else do I buy? Okay. If I buy milk and diapers, I want to put them together on the store, right? So that's the kind of application they're thinking about. They're using transactional data in order to understand, you know, what are customer patterns and use that for business purposes. Now, coming back to statistics, so you remember the development of the bootstrap, right? The Afron paper, that was before what year was it? 1970? 79, right? So that's sort of a whole area of resampling inference, right? In that, you know, in using, and not just because we have computing power. MCMC, that was another big development, right? This is the breakthrough that really made it possible to use Bayesian methods in a more realistic way, not just the usual limited assumptions that we make, right? So we have a whole bunch of other things. LOAS, splines, Mars. And then the ensemble methods that now are very popular, right? Ensemble methods means you actually do a lot of, you sort of average a number of different things to come up with a better predictor. Well, one can argue that that's more in the machine learning domain rather than statistics, but of course now machine learning and statistics, the boundaries are becoming rather blurred. So AdaBoost was developed by Shafir and Freund. Now there's this very nice paper by Friedman on gradient boosting methods, which generalizes AdaBoost, which talks about just not the 0, 1 or the particular loss function used for binary data. You can also do regression type problems, because the program is random forest. And then the other thing is that more and more we're getting more complex data networks. Okay, and I think you guys are going to talk about networks right after my talk. And high dimensional inference that Professor Bose talked about, be much bigger than N, driven by a lot of applications in genomics, for instance. So all of this started happening around the 1980s and so on. So as I said, many of these developments go back to the 1980s. So while we were there, I assume a lot of you are statisticians, and some of you are computer scientists. I'm not trying to make a big deal of this difference, but it's true that there are lots and lots of important issues related to big data or massive data that we did not get into, and things like database management. We always assume, and we teach students, that somebody gives us the data. Somebody gets the data, collects the data, cleans it up, and gives it to us in a form that we analyze the data. Okay? And that's never the case. So computer scientists were much closer to the data, and because of that, they were more looking at database management issues and computing issues, and so once they were doing computing and database management issues, they started thinking about how can I do the analysis? And that's how these people with machine learning techniques came out. A lot of that also was developed by labs, which Shapiro was at Bell Labs. He was at Princeton. I think he went to Microsoft recently. And Batman came up with support vector machines. He was at Bell Labs too. Okay, so what is new with big data? Clearly, the big thing is the huge increase in scale in the so-called 3 V's that people talk about: volume, variety, and velocity. And there are other V's that people have come up with, like veracity, and I don't know what else the V's are. People have come up with different things. So volume, as the name suggests, is just the massive increases in the data, but in the size of the data. But the thing that I'd like to emphasize is there are lots and lots of smaller data sets too these days, right? Because if you have these Fitbits or wearables, you go to a gym, you're collecting lots and lots of data about yourself. So the data capture technologies are making available not just high volume of data, but lots and lots of small data too. Variety refers to the unstructured data like text, image, and so on, which raises a whole bunch of issues about how do you analyze data, how do I extract interesting and important and relevant features, right? How do I model them, and so on. And velocity, of course, it is the particular instance here is streaming data. Data just goes by so fast that you cannot actually collect the data. Okay? You cannot look at snapshot of the data. So that is raising a whole bunch of interesting questions. For instance, a simple question is, how do I compute a quantile? How do I compute a median of streaming data? It's not something that you can do exactly. You can have to come up with a approximate algorithm for computing, just because you can't store the data, you cannot solve the entire data. So you have to worry about how do I compute these things. So a whole bunch of interesting questions and algorithms that come up. Okay. The other thing is, I just, again, from this McKinsey report, just amazing fact, $600 to buy a disk drive that can store all of the music world. Isn't that amazing? How cheap storage has become. Okay. And they're not just data storage, but data transfer as well, because that's the important part of it. So there's a lot of excitement about the potential of big data or data in industry, government, and academia. Particularly in industry, people think that what kind of competitive advantage does it give you? It's all about making money. So the other aspect of this is that, used to be we collected data because we had a particular problem of interest. But now data are becoming available to us. Okay? Somebody is collecting data. Twitter, clickstreams, internet data or different forms. And there is potential usefulness in this data, so data are becoming commodity. So pretty soon they may be traded, right? So it's the commodity of interest for its own sake. In fact, that's what's happening, right? People are actually paying for data from different sources and using this data for various things that they want to do. So of course, I'm going to talk about much faster paced developments in database management, high performance computing, algorithms, and so on. And the funding, of course, is also becoming a lot. And I assume it's also the case in Mexico, right? It's a lot of funding from federal funding, government funding, and so on. But the other thing about this, you got to be very careful. There are a lot of consultants out there trying to make money. And there's a lot of hype. So the kinds of things that I hear and read is, I mean, it's just incredibly silly what they're claiming that big data, so-called big data and analytics can do. Okay, so I'm actually going to skip this part. I'm just going to tell you a little bit about some of these things. I was going to spend a bit more time. So depending on who you talk to, different people tell you different kinds of applications. There are lots and lots of interesting applications. For instance, recommender systems. Okay, you all saw the big Netflix competition about $1 million prize, and if they can actually, who comes up with the best algorithm? The final algorithm that actually won was a combination of several different algorithms, and there were several people who won it. One of them were involved people from HP, people from AT&T Labs, and a number of people, and I've heard some talks about what it is that they do. Pattern recognition is a huge problem now, right? Of different kinds. Now, there are these algorithms called deep learning algorithms that you've heard about. Deep learning is just a artificial, we all heard about neural networks in the 1980s, okay? And they're making a big comeback now because the increased computing power allows us, that means that we can actually have many more layers, okay, and many more nodes. And these deep learning algorithms are so flexible that people for instance, things like face recognition, computer vision, for instance, anything that people do using subject matter expertise, these things is speeding pretty much better, okay? The problem with that, and I mentioned, is that these are black box algorithms. You don't really know what's in it, right? Just like this Watson, IBM Watson machine that is going around beating, I don't know if you have watched Jeopardy, where they actually these two guys who have done so well in Jeopardy. I mean, that part is not so hard because it's just the biggest part there was voice recognition was the biggest part because it's got a huge database of facts and you can look it up much faster than any human can. Okay? So the question there was whether it can actually understand what Alex Trebek says, the host of Jeopardy, and then quickly parse what he says and try to map it in real time into his database. But now they are using Watson in medical research to understand what has been done, what kind of past patterns have been found. So I think there are some teams in the US that are working using Watson to improve the medical research. So the things that these are some things that I know about. Personalized medicine, my colleague at Michigan called Susan Murphy is doing a lot of interesting work on these wearables. The particular area is behavioral intervention. So the idea there is that you are wearing something, it's a bit like a Fitbit, but actually it's smarter. And you can actually send, you can actually read your pulse and send various kind of informations and can transmit data to a remote location. And for the remote location, you can tell the person that it looks like your pressure levels are high, maybe you should take a walk or do different kinds of things. So a whole bunch of things are happening in that space of personalized medicine. I'll skip electronic medical records. Transportation is a big area of focus right now, right? Everybody is talking about autonomous transportation. But even with autonomous transportation, the vehicles, the cars, are now much more electronic systems than mechanical systems. Most of them are more electronic than mechanical systems. So the idea of vehicles communicating with each other, trying to understand traffic patterns, trying to avoid traffic jams, that's one of the big areas. One of the things that people talk about, some years ago, 2-3 years ago, you remember there was a big, lot of people in Shanghai for New Year's Eve and a number of people died. Okay. So one thing that people said is that if they were monitoring the number of sensors, iPhone sensors, they would have known that there were too many people in that particular area, and they could have actually done and anticipated problems like that. So a whole bunch of things like that are going on. Large-scale anomaly detection. Okay? And I'll mention that quickly, and then I'll talk a little bit about this because that's an interesting. To me, this is where a lot of people are excited about big data. Okay? So, for instance, data networks. I mean, pretty much everything that we used to send, phone calls and everything has become data now, right? So one of the things that you might be interested in is monitoring the quality of a data network. This is a data network for a particular real company that's in the US. And what they might be interested in is monitoring the quality of this network and looking at whether are there any segments here where there's degraded quality of transmission. And they want to be able to detect that quickly, and then based on that, they would actually want to reroute traffic, for instance. And that's a very large-scale problem. And the difficulty with this is that, how much you guys know, and you send an email, and you send an FTP, or send something, a file, it's broken up into something called packets. Okay? Many packets with header information, and then they regrouped together. And a lot of these packets can get lost because the buffer is a finite buffer, and the system is very harsh. If it exceeds the finite buffer, it just drops the packet. And so the sending node is waiting for an acknowledgement. If it doesn't get an acknowledgement a certain amount of time, it's going to send it again. And there are priorities. For instance, online messages have higher priority, emails, for instance, have lower priority, and so on. So anyway, this is an area that I've done some work. So fraud detection is again a big thing. For instance, think about a bank that's monitoring your credit cards. Okay. And they have very simple rules. One of the simplest rules that they have is that if somebody using a credit card goes to a gas company, petrol company, and buys $5 worth of petrol, and then pretty soon after they actually have a $5,000 worth of electronic equipment, that's the trigger for them. Usually means that's a fraud, okay? So simple rules. But the problem is a lot of people who are doing fraud know these things, so they're actually trying to be clever. So you have a fraud, when you have a normal behavior and you have a fraud behavior, if you're a very smart fraudster, you would try to be as close as possible with the fraud distribution. So, and how do you detect this anomaly? That's a really difficult and interesting problem. A lot of banks are doing those kinds of work. So a whole bunch of things. I just wanted to talk about this fake news monitoring, right? You guys heard about fake news monitoring? Facebook was under attack recently because a lot of the news, there were people who were creating news that were fake news. Okay. And this got taken up by various Twitters and other places. And so Zuckerberg came in and said, no, this fake news cannot have affected the election, who knows, right? But more recently, Facebook is taking much more stringent actions on these kinds of things. So think about Facebook, fake news monitoring. How do you do that? It's an incredible amount of stuff. It's very similar to complaints monitoring. When you have a large complaint, large database, and you want to look at what kind of complaints are people making. Okay. It involves text mining, obviously, but what other algorithms do you use? So I'm going to only talk about problems. I'm not talking about solutions, because as you get older, you only know about problems. You don't know about solutions. Okay, now I want to talk a little bit about this particular application that my colleagues at Michigan did. And this is really one of the more exciting areas in database. Let me just talk about it and come back and sort of wrap it up. So if you're doing, let's say, working for INEGI here, INEGI, right, is your, or Census Bureau or Bureau of Labor Statistics or whatever in the US, a lot of times the way you collect data, analyze data, and look at unemployment rate, inflation or whatever, is by doing surveys. Okay, you collect data, you do surveys, and then you analyze the data, and by the time the data becomes available, it's like 3 months old, 6 months old. So it's, and the thing has moved on, right? So people are saying, look, I don't really want to know about 3 months old information. I want to know what's happening now, right? And that's what people call nowcasting. Right? That's a term that has been around. Nowcasting, backcasting, going back. Where are we with all these things? Why didn't we come up with this? So here, the example here is what my colleagues at Michigan did. They were econometricians. So they wanted to use social media to measure labor market flows, in particular unemployment. Okay? So they wanted to measure, they used Twitter data to create indices for job flows, job loss, job search, and job posting. So they look at Twitter, so they looked at, this is, like most research, it's always, it's always done after the fact, right? So they looked at data from July 2011 to November 2013. Look at 10% of all Twitter data. This talk about 20 billion tweets, 44 terabytes of data. And the hardest part comes is now taking this data, which is really, a lot of it is just garbage, right? You have to now mine this data in order to understand, in order to extract relevant information. For instance, they were interested in unemployment. So they used words like fired, lost my job, looking for a job, canned, right? Things that are sort of colloquial terms. And then they use what's called K-grams, just not a single word, but K words continuously. And they use these to clean the data, which is of course the hardest part in big data. And based on this, they came up with an indicator of unemployment data. So in the US, what we do is we look at unemployment insurance claims, and that's how we know what the unemployment indicator is. And that's a few months late. So here is the data. So what you see here is in black is the actual claims, and the blue is what they came up with based on social media data. Okay? Now you can see that it doesn't capture everything, right? It captures this peak, there is a false peak, but it captures the overall trend, and you're not going to get the level correct. You're not going to get the level correct because you're looking at two different types of data. Okay? What they're interested in patterns, trends, okay? Peaking, going downwards, going upwards, that sort of stuff. And so you can see that they got this correct, at least reasonably correct, right? So this is one of the things I'll mention about big data. One of the most exciting things about big data that people are interested in excited about is not data that they collect by themselves. For instance, physicists collecting data at CERN, astronomers collecting data using big telescopes. These are all things possible because the technology has become bigger and better. But they are collecting the data, they know what's involved. But what's exciting for a lot of people is data that are already available. Okay? That is Twitter data, Facebook data, clickstream data, for instance. Okay? Data collected for some other purpose. Okay? And we want to know, is this data useful for me? Okay? And I'll talk about some of the issues related to that. That's really where a lot of it's at. Okay? So what are the challenges? So I'm sort of not really doing justice to this. There's lots and lots and lots of work talking about how to make data management efficient, distributed storage, cloud storage, and all of those things happening. So I'm not really qualified to talk about that. Data connectivity is a big issue because a lot of your databases are sitting in remote locations, and so you have to be able to connect the data. You don't want a single repository of data when they're actually distributed. So you want to be able to connect with your databases fast. Distributed processing, right? That's again goes to distributed storage. And these are all, a lot of, you guys must have heard about Apache, which is a non-profit service, and they have the Apache Hadoop, Apache Spark. MapReduce was something, I think originally it was developed at Google, but now Apache is doing something. So this is for distributed processing, simple things like, simple summary statistics. There are lots and lots of players also, open source, vendors. So this is something I was going to talk about because so I have a group of people in Wells Fargo who do advanced data analytics and also advanced computing platforms. And so this is a system that we have developed in-house. I'm going to talk about that. Let me just say high performance computing. So there are many, many solutions for high performance computing, right? So the computer scientists are really, really smart. So for instance, the issue of doing things in memory, for instance, is like Spark does. Coming out scalable algorithm, distributed algorithms, approximate algorithms, just because there's so much data, approximate or randomized algorithms, but this is good, it's doing it exactly. A whole bunch of areas of data curation, a whole bunch of privacy, security. So there are lots and lots of interesting stuff going on right now. So I'm hardly qualified to talk about it. Let me quickly say something about the kinds of things going on in our area. So one of the biggest things is people are getting excited about big data. Okay? The problem with big data is that it's not representative. Often it is not representative. So you might have lots and lots of data, but you don't have data in every space that you're interested in. There are lots of little data in interesting areas. So how do you do and understand? So the issue is really not as much variability or precision, but it's more bias. What's the nature of the bias in the data I have? To understand that, automated algorithms are not going to be able to get that point. You really need subject matter expertise, how the data are collected, and how is it relevant for your purpose. Right? So there's a fair amount of activity. People are now talking about a lot of the techniques developed in causal inference. Simple things like reweighting, what people call covariance matching. You have a set of data, your population of interest, you match the covariance, so you weight according to the covariance that you're interested in. Propensity scores. So, but the problems I think are much more complicated. My own view is that this big data is not going to replace formal inference, because if I wanted to estimate something, and I want to know the bias and I want to know the error bars about variability, I still need to collect the data according to some representative mechanism. Okay? So can we do that? I don't know. But can we do that using big data? I don't know. I think a lot of this big data are exciting because they are useful for generating interesting hypotheses. They're useful for looking at trends. So look, it's going down. And you can safely say, well, it's probably going down the entire population. So it's going up or whatever. Okay, can I find something interesting? And then can I pursue that by collecting additional data? So it may well be that for doing formal inference, we don't have to collect as much data as we used to. We can supplement big data by formal inference. But I don't, in my view at least, formal inference is not going to go away. Again, the role for formal inference. Now, all right. So a bunch of other things. Let me just raise some issues here. One of the things that if you work with big data, and we in the bank, we have billions of records, billions of accounts, 400-500 covariates that we're trying to understand what are the important covariates. So when you have lots of data, what happens is that everything is significant. Everything is statistically significant. You try to do any kind of test of hypothesis, everything is significant. But it's a big difference between statistically significant and being significant from a subject matter point of view. So what is the role of hypothesis testing? A confidence intervals now. So what I think is that testing with fixed alpha doesn't make sense anymore. You have more and more data, you've got to let alpha go to 0. You've got to let alpha go to 0 at a rate. Okay? So that you don't have power for every hypothesis, because you're more and more able to say that close. Right? So I think that I'm sort of thinking about some ideas here. The other thing is that precision, which is more about variance. The big issue here is bias rather than variance. But the other thing we can do with big data is that we can divide it into different pieces, whether in some systematic way or random way, and ask ourselves, is our inference stable across these multiple random subsets of the data? So stability of our inference is probably more interesting than precision. And as I said, bias is also another big issue, which really is a hard problem to do. The other thing is prediction. Okay? So there's a very interesting paper by Bryman about 15 years ago. The two cultures of statistics. Have you guys seen this? It's a statistical science, right? Richard, do you remember this? Yeah. So he argued that a very high proportion of the problems that we have to deal with are prediction problems. Estimation, understanding variable selection, understanding the system, what's an important variable, what's not important variable, they're not as important. So it created a lot of controversy in this. But if you look at machine learning algorithms, they're all about prediction. Okay? They're all about prediction, right? And many of them, especially these ensemble algorithms, where you apply, you sort of get many different predictions and you average them. Those are really, really black box algorithms. Okay? So, and they're doing really, really well in many situations. But for instance, in the bank right now where I am, the regulators do not want black box models, at least as of now. They want to know what is the input and output, which are the models which are the variables in your model, how did you develop the model, how important is this variable, because they want to know that people are not gaming the system. Because you can actually do all kinds of illegal things, right? So there's a lot of emphasis on what you might call system identification. But there's an interesting, very interesting question is, what is the role of black box machine learning techniques, and can we increasingly make them white box or non-black box? Open them up, so to speak. So there are a whole bunch of things that I'm going to skip. I talked about this already. So I like to separate the kinds of data into these two categories. Primary data, which means you are collecting the data, you or somebody, some people associated with this are collecting the data with some specific goals and hypotheses match. The population of interest is clear, okay? And the data access is clear. People who collect, analyze, make conclusions are typically owners of the data. Issues related to data security, data sharing, all of those things maybe have been thought out, at least handleable because you control the data. Okay? So bias in the name may also be well understood. The other kinds of data is what I call secondary data. Data already available like social media data. Data are collected for different reasons. They may contain useful information for your purpose, particularly in official statistics. A lot of official statistics agencies are very excited about this kind of thing. The question is, you don't really know how useful it's going to be because the degree of usefulness varies. So the question is that should I invest a lot of money getting access to this data, cleaning it up, and looking at it, right? There's a lot of uncertainty associated with that. Lots of problems with the data. Lots of missing data, sparse information, duplication, so signal to noise ratio can be small. The other thing I probably alluded to is lots of possible biases, because the data are not collected for inference in your particular population. Being collected by somebody else. Okay? And of course the biggest issue is correlation versus causation. I'll mention that in a second. Okay? The other thing is that the data access is going to be a big problem, because a lot of the data are not owned by you. Data on your Twitter or somebody else, and even Google data. A friend of mine was trying to do some research on trying to identify who co-authors papers with whom. So he was trying to download papers from Google Scholar to talk about, to do this. But after about 50 downloads, Google apparently shut him down because they don't really want you to download too much data because they might think that you're doing it for some other purpose. So, right. So I think that this kind of data are useful for finding interesting information, patterns and trends, okay, and not necessarily follow it. Finally, big data means end of scientific theories, right? So there's this quote by this guy, Chris Anderson, in 2008. You throw enough data in an advanced machine learning technique, and all the correlation relations simply jump out. You'll understand. So you don't really, right? Well, this view was was very much in vogue in around that time. So if you look at things, for instance, there is a nice book called Spurious Correlations by this guy Tyler Biggin. I recommend that you take a look at it. So here is a correlation of revenue generated in arcades. Arcades where you play games, and computer science doctors. You can see how the two curves. And here, U.S. spending on science, space, and technology, and suicides by hanging, strangulation, or something. It's a website. Yeah, it's a website, but it's also in this book. So, so we all know that fishing for correlations will not explain what is really happening. A lot of spurious correlation. I like this one. It says, we found the correlation in the data. Sales with the shaved heads. That's everyone being a racist. So I think, Richard, you're ahead. So having more data won't substitute hard thinking, hard recognizing anomalies, and exploring the truth, right? So I should stop here. Right. Okay, what's happening? I want to talk about data science a little bit. Because everybody's talking about data science. By the way, if you're a statistician, don't call yourself a statistician, call yourself a data scientist. Your salary would be like 30 to 40%. Seriously. Nobody's looking for statisticians anymore. They're looking for analytics people, right? And data scientists. Right? It's the same thing. Well, it's not the same thing. Okay. A lot of exciting. So what is data science? What's the difference between statistics and data science? Is it really science or is it engineering? So let me just talk about that. Okay. Oh, I'm missing a slide. I'm missing several slides. Okay. So if you look at the definition of data science, in Wikipedia it says a generalized method for extracting knowledge from data. That's what Wikipedia says, okay? But then you say, but that's what statistics has been. Right? What is the difference, right? This is a problem, right? People are rewriting, in Google is an open source thing, right? People are rewriting it. So if you go back and look at, look at Wikipedia, you'll say the earliest use of the word data science seems to go in 1976, used by a guy called Peter Nair in New York. And he used the term for data processing. This computer science data process. And then around the early 1990s, two of my colleagues, Bill Cleveland from Bell Labs and Jeff Wu, who was in Michigan, they used the word data science. There was a paper in International Statistical Review, 1993 by Cleveland, and Jeff Wu talked about it in a general lecture. It's about talking about statistics, but in a broader sense, data collection, data analysis. So in a sense, going in the direction of what it is right now. So I've been involved in creating this institute in Michigan for the last 4 years. So we came up with a definition, with a working definition. Concepts, methods, and algorithms involved in collecting, curating means cleaning, and all kinds of things that goes with it. Managing, analyzing, and transforming data information into information to enable knowledge creation, decision making, and a variety of applications. So this definition, of course, I don't think is going to be taken up by Wiki. but for us, it captures lots of things that's going on. So data science is really a combination of relevant information from multiple fields. Okay? Statistics and mathematics clearly, but computer science and information science and domain knowledge. And there is a Venn diagram by a guy called Drew Conway. You want to look at Google for data science. He has statistics and math, computer science, which is really hacking skills, and machine learning, and then there are these things, and then there is an intersection. He calls the intersection of data science. I don't think it's an intersection because it's actually more like a union. Okay? And it's more, parts of computer science are relevant. Okay? Parts of statistics are relevant. Parts of mathematics and optimization are relevant. Right? So you have techniques that we can get from different areas. So for instance, we have an undergraduate degree in data science that is offered jointly by our stat department and computer science department. So in the computer science side, they teach a lot of database management skills, algorithms, those kinds of things. So for us, we teach a lot of basic statistical theory, but we also teach machine learning or statistical learning techniques, we teach regression, we teach predictive analytics, and so on. So to me, data science is something that takes lots of relevant things from different fields, combines with domain knowledge. But the hard part about this is a lot of people, particularly in the computer science field, are skipping this part and going to automated algorithm to do things. And I really think in the long run, that's going to be not right. So as I said, data science is more than statistics in the sense that it includes lots of statistics, but it also includes parts of computer science. The other thing I want to quickly mention is that science versus engineering. Okay? So if you actually work as an applied statistician and you deal with big data, something like 60 to 70% what you do is data processing, data cleaning, moving data from different sources, looking to see whether they are clean or not, are they missing data, all that stuff. All of that is not science, by the way. It's really engineering, right? And all of that, is very hard to duplicate that too. It's very labor-intensive work. So a lot of what goes on as data science, to me, is really engineering. Okay? But the word data science is caught on. So, which is fine, especially if they pay you more than data engineering. Okay, we have a University of Michigan Data Science Institute. I'm going to skip this. I was the co-founder of this institute. We've got $100 million lots of activities. You can just Google for that. And there are lots and lots of things happening in this space. Many, many initiatives on big data science and big data in other universities, industry, and the foundations are funding these things. Lots of hype and false advertising too, right? So that goes with any kind of popular things. So we went through this whole new category, but there's a lot of interesting stuff for us, both statisticians, computer science, particularly in collaboration, to work on and trying to understand information, extract information from huge amounts of data. A lot of it is noisy, low signal to noise ratio. So with that, let me just, there is a book by Microsoft guys called The Form Paradigm, Data Intensive Scientific Discovery. So we've heard of the book called by Thomas Kuhn called The Structure of Scientific Revolutions. There are 3 paradigms in here. These guys say data science has emerged as the 4th member of scientific discovery. Okay? All right, with that I'll stop. Thank you.